Whoa, you almost got hit by a banana. Just goes to show you, math can be dangerous sometimes. And today, it's going to be a little on the dangerous side, Oshkosh North. We're in lesson 5-2, day 1. And for our example, for who will win the last banana, you are on a desert island playing dice with another castaway. The winner's prize will be the last banana. Here are the rules of the game. Each player rolls a die. If the largest value shown is a 1, 2, 3, or 4, then player 1 wins. If the largest value shown is a 5 or 6, then player 2 wins. It doesn't matter who gets the 5 or 6. If somebody gets a 5 or 6, or if both people get a 5 or 6, player 2 wins. If both of them get a 1 through 4, player 1 wins. So, what do you think? Who do you think has the advantage in this game? Player 1, player 2, or neither? Make your best guess. All right, let's see what's going to happen. So, we're going to do a simulation. We're going to play the game 20 times. And it says play it with your partner in class and everything, but we're on COVID days, so we are virtual. So we're just going to give you the data that happened. So you've got player 1 and player 2, and we keep track of who wins. We roll a die for each player, a number cube for each player, and it turned out that player number 1 won 8 times, and player number 2 won 12 times. So that was 60% for player 2, 40% for player 1. Notice how the probabilities add up to 1. So they're going to be a percentage adds up to 100%. So who won more often? Maybe this was only true for your group. Let's see how the rest of the class did. So now we would add the rest of the class in and see what happened. So this was the data for the entire class. The number of times player 1 won was 138 out of 320 times for 43% or 0.43. The number of times player 2 won was 182 out of 320 for 57% or 0.57. So these two would add up to 1. And they're complements of each other, because the probability of 2 winning is 1 minus the probability that 2 didn't win. So, that's how you can figure that out. This is called an experimental probability because we ran an experiment to try to figure out what the probability was. Now, in this case, there is a way you can do theoretical probability. And if you were to look in your textbook, you will find this chart. And this chart is what we're going to use to decide who wins most often theoretically. So these are your rolls over here, 1 through 6 for one player, 1 through 6 for the other. The part that's highlighted in blue would be where player 1 wins, where nobody rolled a 5 or 6. Player 2 wins all of these in green. So all those in green would be player 2. There's 20 of those. And there's 16 in blue. So if they're asking you for the probability that player 1 wins, in theory, that's going to be 16 out of 36, 4/9, or 0.44, repeating 44.4%. Which was close to the probability you found in 4A, your group data or the classroom data? Why do you think that is? Well, you got the law of large numbers working for the classroom data. So it's probably going to be closer to the theoretical, but because you're running more trials. The class data, we're going to play a lot more games. So you're going to have a lot more data. This is called a sample space. It's a list of the possible actions that could happen. And in this case, that would be your theoretical, and it's also in your book. Now let's take a look at something cool. For this, let's consider something that you're going to have coming up in the future. What do you think the probability of a player winning is going to be? Well, let's say that you were player number 2. Okay, so what's the probability that you're going to win if you're player number 2? Well, if either player rolls a 5 or if either player rolls a 6, you win. So if you're rolling your number cube and you get a 5 or a 6, you win. If you don't, it doesn't mean you automatically lose. It means you got to take a look at the other player's die. So that's 2 out of 6, or that's a 1/3 chance of that happening. Then you're going to check the other player. The other player has the same 2/6 chance of rolling a 5 or 6. So that's another 1/3. So that's 1/3 plus 1/3. Now, there's also a chance that both of you rolled a 5 or 6. So if we subtract the probability that both of you rolled a 5 or a 6, that's 1/3 times 1/3. And we figure this out mathematically. We get 2/3 minus 1/9. This is the probability of 2 wins. Player 2 wins. So 2/3 minus 1/9, that's going to be 6/9 minus 1/9, which is 5/9. So it's a probability of 5/9 that 2 is going to win. Probability that 1 wins would be the complement of that. 9/9 minus 5/9 would be 4/9. And the probability that 2 wins is 5/9. If you want to write them as decimals, you're looking at 0.4 for repeating, and here would be 0.55 repeating. So let's see how that worked with comparing to our theoretical. The probability that 1 would win is 44%. Hey, there it is. There it is. What do you think of that? That's the theoretical probability, and that's how you can figure them out. So let's take a look at your notes for vocabulary and stuff like that. So we're going to start with the big idea being a probability model. It's a list that shows all possible outcomes and their probability. So like that list, this is a probability model right here of all the dice. That also is on page 342 in your book, the 2 dice outcomes. Probabilities must add up to 1, and each probability is between 0 and 1. So it could be 0, it could be 1. 0 is impossible, 1 is certain, and it's almost always going to be something in between. So between 0 and 1. So complementary, that the probability of an event not happening is a complement. The probability of a complement means that A isn't going to happen is 1 minus the probability that A does happen. Let's take a look at an example. How about if we consider the probability that it's going to rain today is 20%. The complement of that is the probability that it's not going to rain today. So the complement would be 80%. If it's the chances of it raining are 20%, the complement would be 1 minus 20% or 80%. Then we've got this concept of mutually exclusive events. Mutually exclusive is when events cannot occur together or at the same time. So some examples might be you get to the end of a road and it's a crossroad and you got to turn left or right. You can't do both. You got to make a choice. If you're flipping a coin, you're either going to get heads or tails. You can't get both at the same time. If you're rolling 2 dice, like we just had that list, well, you're either going to get an even total or an odd total. You can't get anything else. They're mutually exclusive. How about if you're selecting a card from a deck and it wanted to figure out heart or a diamond? Well, you can't get both a heart and a diamond. There's no heart diamonds. So those are all mutually exclusive things. So you're probably wondering, well, what isn't mutually exclusive? Well, how about if you had a deck of cards and you want to figure the probability that you either selected a heart or a face card, then that could happen. That's not mutually exclusive because you could have a heart that is a face card. So it could be like the King of Hearts, the Queen of Hearts, and the Jack of Hearts. Those would all fulfill both conditions of being a heart and a face card. So that's when it's not mutually exclusive. And you're going to wind up doing some Venn diagrams when you get to that. And you'll have the middle of the Venn diagram will be what is in common. All right, so let's take a look, check for understanding today. Pew Research Center reported that among mothers, family size is shrinking. Suppose we are to randomly select one mother age 40 to 44 and record the number of children she has. Here is a probability model. Okay, so here's your model. If she has one child, it's 22%. Two children, it's 41%. Three children, probability is 24%, and four children or more would be 13%. Now, I know what you're thinking. You guys are brilliant students, and you're probably already mentally figuring this out in your head and going, hey, that adds up to 1. It can't happen because what if she has 0 children? There's a lot of people who have 0 children. So how can that add to 100%? Well, here's the key. Sometimes one word changes a question. So this is just dealing with mothers. So if they don't have a child, they're not a mother. Once a woman has her first child, then she becomes a mother. So that's why they have this stipulation adding up to 100%. Okay, well, anyway, these are the percentages that you're given. Explain why this is a valid probability model. Each probability is between 0 and 1. Each of these separately is between 0 and 1, and the probabilities all add up to 1. Explain why the events have one child and have 2 children are mutually exclusive. Well, you can have one child or you can have 2. As soon as you have the second child, you're now in this category of having 2. It's not like we're going to add on. So let's see what we got for the probability. Find the probability that a randomly selected mother has less than 2 children. So less than 2 children does not include children because it doesn't say less than or equal to. That's why you got to be very careful. It's kind of dangerous in math. You got to read all the words. And if there's a word left out like less than or greater, this is just less than. So that would be just one child. So one child is the 22% or 0.22, which is what you got right here, 0.22. So that's probably it. The mother had less than 2 children. How about if it was less than 3 children? Well, then you'd add these together. So you'd have 0.63 would be that. But they didn't ask us for that. Actually, they did in Part D. Find the probability that a randomly selected mother has 1 or 2 children. The probability of 1 or 2 children is 0.22 plus 0.41, which is 0.63. So that would be the probability of having 1 or 2 children. Find the probability that a randomly selected mother does not have 4 or more children. So now we're going to be looking at the complement. The probability that she does have 4 or more children is 0.13. That's right here, 0.13. So it's 1 minus 0.13 or 0.87 or 87%. Once again, we want to thank our friends at Stats Medic for coming up with such awesome notes for us for our AP Statistics class. It's Mr. Murphy signing off from Oshkosh North High School. Stay awesome, Spartans, and we'll see you next time.